imagine trying to measure distance on a flat paper map. One ruler works everywhere. Now imagine the map is made of rubber, stretched differently at every point. Suddenly, distance depends on where you stand and which direction you move. That is the core idea of Riemannian geometry. A space carries a moving ruler. The moving ruler is called the metric. In symbols, we write ds squared equals gij of x, dxi, dxj. The tiny step dx tells you your direction. The matrix G tells you how expensive that step is at that location. Add up all those tiny costs, and you get the length of a curve. On a sphere, the shortest path from city to city is not a straight line through the map. It is a great circle, like the routes airplanes trace across the globe. Riemannian geometry calls these shortest possible paths geodesics. Here is the beautiful twist: curvature is not a force pulling from outside. Curvature is information stored in the rulers themselves. If nearby geodesics drift together or apart, the space is telling you it is curved. That is why this language powers general relativity. Matter changes the metric. The metric changes which paths are straight. Planets orbit because, in curved spacetime, their natural straightest paths look like curves to us. So the next time you hear metric tensor, do not picture a monster equation. Picture a field of tiny smart rulers, one at every point, quietly deciding what distance, angle, and straightness mean.